The unfortunate fact about physics is the takeoff is easier than the landing.
Yeah,
It seems.
yes.
And you mentioned Starship. One of the incredible engineering feats that you get to see is the reusable rockets that take off, but they land, and they land uh, using control, and they do so perfectly. And sometimes when it's synchronous, it's beautiful to see. And then with Starship, you see the the chopsticks that catch the ship. I mean, there's just so much incredible engineering. But you mentioned Starships is somehow helpful here. So, what's your hope with Starship? What kind of science might it enable, possibly?
There's two things. I mean, it's the launch cost itself, which is hopefully going to mean per kilogram, it's going to dramatically reduce the cost. If it's the sort of the level, even if it's a factor of 10 higher than what Elon originally promised, this is going to be a revolution for the cost to launch. That means you could do all sorts of things. You could launch large telescopes, which could be basically like JWST, but you don't even have to fold them up. JWST had this whole issue with its design that it's 6.5 meters across. And so there's no fuselage, which is that large at the time. The Ares 4 wasn't large enough for that. And so they had to fold it up into this kind of complicated origami. And so a large part of the cost was figuring out how to fold it up, testing that it unfolded correctly, repeated testing. And, there was something like 130 fail points or something during this unfolding mechanism. And so all of us were holding our breath during that process. But if you have the ability to just launch, arbitrarily large masses, at least comparatively compared to JWST, and very large mirrors into space, you can more or less repurpose ground-based mirrors. The Hubble Space Telescope mirror and the JWST mirrors are designed to be extremely lightweight, and that increased their cost significantly. They have this kind of honeycomb design on the back to try and minimize the weight. If you don't really care about weight because it's so cheap, then you could just literally grab many of the existing ground-based mirrors across telescopes across the world, 4 meter, 5 meter mirrors, and just pretty much attach them to a chassis and have your own space-based telescope. I think the Breakthrough Foundation, for instance, is an entity that has been interested in doing this sort of thing. And so that raises the prospects of having not just one JWST that just, JWST is a fantastic resource, but it's split between all of us, cosmologists, star formation, astronomers, those of us studying exoplanets, those of us wanting to study, the ultra deep fields and the origin of the first galaxies, the expansion rate of the universe. Everyone has to share this resource, but we could potentially each have, one JWST each that is maybe just studying a handful of the brightest exoplanet stars and measuring their atmospheres. This is important because if we talked about this planet TRAPPIST 1e earlier, that planet, if JWST stared at it and tried to look for biosignatures, by which I mean oxygen, nitrous oxide, methane, it would take it of order of 200 transits to get even a very marginal, what we'd call 2.5 sigma detection of those, which basically nobody would believe with that. And 100 transits, this thing transits once every 6 days. So you're talking about sort of 4 years of staring at the same star with one telescope. There'd be some breaks, but it'd be hard to schedule much else because you have to continuously catch each one of these transits to build up your signal to noise. And so JWST is never going to do that. In principle, technically, JWST could technically have the capability of just about detecting a biosignature on an Earth-like planet around a non-sun-like star. But still, impressively, we have basically the technology to do that, but we simply cannot dedicate all of its time practically to that one resource. And so Starship opens up opportunities like that of mass producing these kinds of telescopes, which will allow us to survey for life in the universe, which of course is one of the grand goals of astronomy.
I wonder if you can speak to the bureaucracy, the political battles, the scientific battles for time on the James Webb Telescope. There must be a fascinating process of scheduling that. All scientists are trying to collaborate and figure out what the most important problems are, and there's an interesting network of interfering scientific experiments probably they have to somehow optimize over.
It's a really difficult process. I don't envy the TAC that are going to have to make this decision. We call it the TAC, the Time Allocation Committee, that make this decision. And I've served on these before, and it's very difficult. Typically for Hubble, we were seeing at least 10, sometimes 20 times the number of proposals for telescope time versus available telescope time. For JWST, There has been one call already that has gone out. We call it cycle 1. And that was oversubscribed by, I think, something like 6-1, 7-1. And the cycle 2, which has just been announced fairly recently, and the deadline is actually the end of this month. So my team are totally laser focused on writing our proposals right now. That is expected to be much more competitive, probably more comparable to what Hubble saw. And so it's hard.
More competitive than the cycle 1, you said already? Because that's already
more
super
competitive than the first cycle. So I said the first cycle of James Webb was about 6-1, and this will probably be more like 20-1, I would expect.
So these are all proposals by scientists and so on, and it's not like you can schedule at any time. Because if you're looking for transit times,
you have a time critical element. To
time critical element, and they're conflicting in non-obvious ways because the frequency is different, the duration is different. Right. There's probably computational needs. Yeah, they're different. There's the type of sensors, the direction pointing, all that.
Yeah, it's hard, and there are certain programs like doing a deep field study where you just more or less point the telescope, and that's pretty open. I mean, you're just accumulating photons. You can just point at that patch of the sky whenever the telescope is not doing anything else, and just get to your month. Let's say a month of integration time is your goal over the lifetime of JWST. So that's maybe a little bit easier to schedule. It's harder, especially for us looking at cool worlds, because as I said earlier, these planets transit very infrequently. Mm-hmm. So we have to wait. If you're looking at the Earth transiting the sun, an alien watching us, they would only get one opportunity per year to do that observation. The transit lasts for about 12 hours. And so if they don't get that time, it's hard. That's it. If it conflicted with another proposal that wants to use another time critical element, it's much easier for planets like these hot planets or these close-in planets because they transit so frequently. There's maybe 100 opportunities. And so then the TAC can say, okay, they want 10 transits. There's 100 opportunities here. It's easier for us to give them time. We're almost in the worst case scenario. We're proposing to look for exomoons around 2 cool planets. Mm-hmm. And so we really only have one bite of the cherry for each one. And so our sales pitch has been that these are extremely precious events. And more importantly, JWST is the only telescope, the only machine humanity has ever constructed, which is capable of finding moons akin to the moons in our solar system. Kepler can't do it, even Hubble can't do it. JWST is the first one. And so there is a new window to the universe because we know these moons exist. They're all over the place in the solar system. You have the moon, you have Io, Callisto, Europa, Ganymede, Titan. Lots of moons are fairly similar size, sort of 30% the size of the Earth. And this telescope is the first one that can find them. And so we're very excited about the profound implications of ultimately solving this journey we're on in astronomy, which is to understand our uniqueness. We want to understand how common is the solar system. Are we the architecture that frequently emerges naturally, or is there something special about what happened here?
I think this is not the worst case. It's the best case. It's obvious. It's super rare. So you have to I love scheduling from a computer science perspective. That's my background. So algorithmically, to solve a schedule problem, I would schedule the rarest things first. Yep. And obviously, this is the JWST is the first thing that can actually detect a cool world. So this is a big new thing. You can show off that new thing. It happens rarely. Schedule it first. It's perfect.
You should be in the TAC. This is perfect.
I will. I'll file my application after we're done with this. I this part of me is the OCD. Part of me is the computational aspect. I love scheduling, computing device, because you have that kind of scheduling on supercomputers. On that scheduling problem is fascinating. How do you prioritize computation? How do you prioritize science, data collection, sample collection, all that kind of stuff? It's actually kind of fascinating because data, in ways you expect and don't expect, will unlock a lot of solutions to some fascinating mysteries. And so collecting the data and doing so in a way that maximizes the possibility of discovery is really interesting. Like from a computational perspective.
I agree. There's a real satisfaction in extracting the maximum science per unit time out of your telescope. Exactly. And that's the TAC's job. But the TAC are not machines. They're not a piece of computer code. They will make their selections based off human judgment. And a lot of the telescope, certainly within the field of exoplanets, because there's different fields of astronomy, but within the field of exoplanets, I think a good expectation is that most of the telescope time that JWST have will go towards atmospheric retrieval. which is sort of alluded to earlier, like detecting molecules in the atmospheres, not biosignatures, because as I said, it's really not designed to do that. It's pushing JWST probably too far to expect it to do that. But it could detect, for example, a carbon dioxide rich atmosphere on TRAPPIST-1e. That's not a biosignature, but you could prove it's like a Venus in that case, or maybe like a Mars in that case. Like both those have carbon dioxide rich atmospheres. Doesn't prove or disprove the existence of life either way, but it is our first characterization of the nature of those atmospheres. Maybe we can even tell the pressure level and the temperature of those atmospheres. So that's very exciting. But we are competing with that, and that I think that science is completely mind-blowing and fantastic. We have a completely different objective, which is in our case to try and look for the first evidence of these small moons around these planets, potentially even moons which could be habitable, of course. So I think it's a very exciting goal, but Attack has to make a human judgment essentially about which science are they most excited by, which one has the highest promise of return, the most highest chance of return. And so that's hard, because if you look at a planetary atmosphere, well, most of the time the planet has an atmosphere already. And so there's almost a guaranteed success that you're going to learn something about the atmosphere by pointing JWST at it. Whereas in our case, there's a harder sell. We are looking for something that we do not know for sure exists yet or not. And so we are pushing the telescope to do something which is inherently more risky.
Yeah, but the existence, if shown, already gives a deep lesson about what's out there in the universe. That means that other stars have similar types of variety as we have in our solar system. They have an Io, they have a Europa, and so on, which means like there's a lot of possibility for icy planets, for water, for planets that enable planets and moons. That's super exciting, because that means everywhere through our galaxy and beyond, there is just innumerable possibility for weird creatures.
I agree.
Life forms.
You don't have to convince me. I mean, NASA has been on this quest for a long time, and it's sometimes called Eta Earth. It's the frequency of Earth-like, usually they say planets in the universe. How common are planets similar to our Earth in terms of ultimately, we'd like to know everything about these planets in terms of the amount of water they have, how much atmosphere they have. But for now, it's kind of focused just on the size and the distance from the star, essentially. How often do you get similar conditions to that? That was Kepler's primary mission, and it really just kind of flirted with the answer. It didn't quite get to a definitive answer. But I always say, look, if we're looking, if that's our primary goal, to look for Earth-like, I would say, worlds, then moons has to be a part of that, because we know that Earth-like, from the Kepler data, the preliminary result is that Earth-like planets around sun-like stars is not an inevitable outcome. It seems to be something like a 1 to 10% outcome. So it's not particularly inevitable that happens. But we do often see about half of all sun-like stars have either a mini Neptune, or a Jupiter in the habitable zone of their stars. That's a very, very common occurrence that we see. Yet we have no idea how often they have moons around them, which could also be habitable. And so there may very well be, if even 1 in 5 of them has an Earth-like moon or even a Mars-like moon around them, then there would be more habitable real estate in terms of exomoons than exoplanets in the universe.
So you can essentially 2x, 3x, 5x, maybe 10x the number of habitable worlds out there in the universe. Our current estimate for like the Drake equation.
Absolutely. Yeah.
So this is one way to increase the confidence and increase the value of that parameter.
And just know where to look. I mean, we would like to know, where should we listen for technosignatures? Where should we be looking for biosignatures? And not only that, but what role does the moon have in terms of its influence on the planet? We talked about these directly imaged telescopes earlier, these missions that want to take a photo, to quote Carl Sagan, the pale blue dot of our planet, but the pale blue dot of an exoplanet. And that's the dream, to one day capture that. But as impressive as the resolution is that we are planning and conspiring to design for the future generation telescopes to achieve that, even those telescopes will not have the capability of resolving the Earth and the moon within that. It'll be a pale blue dot pixel, but the moon's grayness will be intermixed with that pixel. And so this is a big problem because one of the ways that we are claiming to look for life in the universe is a chemical disequilibrium. So you see two molecules that just shouldn't be there. They normally react with each other, or even one molecule that's just too reactive to be hanging around the atmosphere by itself. So if you had oxygen and methane hanging out together, those would normally react fairly easily. And so if you detected those two molecules in your pale blue dot spectra, you'd be like, okay, we have evidence for life. Something's metabolizing on this planet. However, the challenge here is, what if that moon was Titan? Titan has a methane-rich atmosphere. And what if the pale blue dot was in fact a planet devoid of life, but it had oxygen because of water undergoing this photolysis reaction, splitting into oxygen and hydrogen separately? So then you have all of the hallmarks of what we would claim to be life, but all along you were tricked. It was just a moon that was deceiving you. And so we're never going to, I would claim, really understand or complete this quest of looking for life, biosignatures in the universe, unless we have a deep knowledge of the prevalence and role that moons have. They may even affect the habitability of the planets themselves. Of course, our own moon is freakishly large. By mass ratio, it's the largest moon in the solar system. It's a 1% mass moon. If you look at Jupiter's moons, they're like 10 to the power minus 4, much smaller. And so our own moon seems to stabilize the obliquity of our planet. It gives rise to tides. Especially early on when the moon was closer, those tides would have covered entire continents. And those rock pools that would have been scattered across the entire plateau may have been the origin of life on our planet. The moon forming impact may have stripped a significant fraction of lithosphere off the Earth, which without it, plate tectonics may not have been possible. We'd have had a stagnant lid because there was just too much lithosphere stuck on the top of the planet. And so there are speculative reasons, but intriguing reasons as to why a large moon may be not just important, but central to the question of having the conditions necessary for life. So moons can be habitable in their own right, but they can also play a significant influence on the habitability of the planets they orbit. And further, they will surely interfere with our attempts to detect life remotely from afar.
So, taking a tangent upon a tangent, you've written about binary planets.
Yep.
And that they're surprisingly common, or they might be surprisingly common. What's the difference between a large moon and binary planets? What are binary planets? What's interesting to say here about giant rocks flying through space and orbiting each other?
The thing that's interesting about binary objects is that they're very common in the universe. Binary stars are everywhere. In fact, the majority of stars seem to live in binary systems. When we look at the outer edges of the solar system, we see binary Kuiper belt objects all the time, asteroids basically bound to one another. Pluto-Charon is kind of an example of that. It's a 10% mass ratio system. It almost is, by many definitions, a binary planet, but now it's a dwarf planet. So yeah, I don't know what you call that now. But we know that these, the universe likes to make things in pairs.
Yeah. So you're saying our sun is an incel? It's looking. So most things are dating; they're in relationships, and ours is alone.
It's not a complete freak of the universe to be alone, but it is. It's more common for sun-like stars. If you count up all the sun-like stars in the universe, about half of the sun-like star systems are in binary or trinary systems, and the other half are single. But because those binaries are 2 or 3 stars, then cumulatively, maybe like a third of all sun-like stars are single.
I'm trying hard to not anthropomorphize the relationship the stars have with each other.
Yeah,
but
the triplets.
I've met those folks also. So is there something interesting to learn about the habitability, how that affects the probability of habitable worlds when they kind of couple up like that in those different ways?
Well, it depends if we're talking about the stars or the planets. Certainly, if stars couple up, that has a big influence on the habitability. Of course, this is very famous from Star Wars. Tatooine in Star Wars is a binary star system, and you have Luke Skywalker looking at the sunset and seeing 2 stars come down. And for years, we thought that was purely a product of George Lucas's incredibly creative mind. And we didn't think that planets would exist around binary star systems. It seems like too tumultuous an environment for a quiescent planetary disk, circumstellar disk, to form planets from. And yet, one of the astounding discoveries from Kepler was that these appear to be quite common. In fact, as far as we can tell, they're just as common around binary stars as single stars. The only caveat to that is that you don't get planets close into binary stars. They have like a clearance region on the inside where planets, maybe they form there, but they don't last. They are dynamically unstable in that zone. But once you get out to about the distance that the Earth orbits the sun, or even a little bit closer in, you start to find planets emerging. And so that's the right distance for liquid water, it's the right distance for potentially life on those planets. And so there may very well be plenty of habitable planets around the binary stars. Binary planets is a little bit different. Binary planets, I don't think we have any serious connection of planet binarity to habitability. Certainly when we investigated it, that wasn't our drive, that this is somehow the solution to life in the universe or anything. It was really just like all good science questions, a curiosity-driven question.
What's the dynamic? Are they legit orbiting each other as they orbit the star?
So the formation mechanism proposed here, because it is very difficult to form two protoplanets close to each other like this. They were generally merged within the disk, and so that's why you normally get single planets. But you could have something like Jupiter and Saturn form at separate distances. They could dynamically be scattered in towards one another and basically not quite collide, but have a very close-on encounter. Now, because tidal forces increase dramatically as the distance decreases between two objects, the tides can actually dissipate the kinetic energy and bring them bound into one another. So that seemed, when you first hear that, you think, well, that seems fairly contrived, that you'd have the conditions just right to get these tides to cause a capture. But numerical simulations have shown that about 10% of planet-planet encounters are shown to produce something like binary planets, which is a startling prediction. And so that seems at odds with, naively, the exoplanet catalog, for which we know of so far no binary planets. And we propose one of the resolutions to this might be that the binary planets are just incredibly difficult to detect, which is also counterintuitive. Because remember how they form is through this tidal mechanism. And so they form extremely close to each other. Sort of the distance that Io is away from Jupiter, just a few planetary radii, they're almost touching one another. And they're just tidally locked, facing each other for eternity. And so in that configuration, as it transits across the star, it kind of looks like you can't really resolve those two planets. It just looks like one planet to you that's going across the star. The temporal resolution of the data is rarely good enough to distinguish that. And so you'd see one transit, but in fact, it's two planets very close together, which are transiting at once. And so, yeah, we wrote a paper just recently where we developed some techniques to try and get around this problem and hopefully provide a tool where we could finally look for these planets.
The problem of detection of these planets when they're so close.
That was our focus, was how do you get around this merging problem? So whether they're out there or not, we don't know. We're planning to do a search for them, but it remains an open question. And I think just one of those fun astrophysics curiosities questions, whether binary planets exist in the universe. Because then, you have binary Earths, you could have binary Neptune, all sorts of wild stuff that would, float the sci-fi imagination.
I wonder what the physics on a binary planet feels like. It might be trivial. I have to think about that. I wonder if there's some interesting dynamics. Like, you feel multiple... Or would gravity feel different at different parts of the surface of the sphere when there's another large sphere? That's interesting.
Yeah, I would think that the force would be fairly similar because the shape of the object would deform to a flat geopotential, essentially, a uniform geopotential, but it would lead to a distorted shape for the two objects. I think they'd become ellipsoids facing one another. So it would be pretty wild. When people like flat Earth or spherical Earth, you fly from space and you see a football-shaped Earth as your own planet.
Finally, there's proof. And I wonder how difficult it would be to travel from one to the other. Because you have to overcome the one. No, it might be kind of easy.
Yeah, I mean, they're so close to each other, that helps. And I think the most critical factor would be how massive is the planet. That's always, one of the challenges with escaping planets, there was a fun paper one of my colleagues wrote that suggested that super-Earth planets may be inescapable. If you're a civilization that were born on a super-Earth, the surface gravity is so high that the chemical potential energy of hydrogen or methane, whatever fuel you're using, simply is at odds with the gravity of the planet itself. And so you would, our current rockets, I'm not sure with the fraction, but maybe like 90% of the rocket is fuel or something by mass. These things would have to be like the size of the Giza pyramids of fuel with just a tiny tip on the top in order just to escape their planetary atmosphere. And so it has been argued that if you live on a super Earth, you may be forced to live there forever. There may be no escape unless you invent a space elevator or something. But then how do you even build the infrastructure in space to do something like that in the absence of a successful rocket program? And so the more and more we look at our Earth and think about the sorts of problems we're facing, the more you see things about the Earth which make it ideally suited in so many regards. It's almost spooky, right? That we not only live on a planet which has the right conditions for life, for intelligent life, for sustained fossil fuel industry, just happens to be in the ground. We have plenty of fossil fuels to get our industrial revolution going. But also the chemical energy contained within those fossil fuels and hydrogen and other fuels is sufficient that we have the ability to escape our planetary atmosphere and planetary gravity to have a space program. And we also happen to have a celestial body which is just within reach, the moon, which doesn't also necessarily have to be true. Were the moon not there, what effect would that have had on our aspirations of a space program in the 1960s? Would there have ever been a space race to Mars or to Venus? It's a much harder, certainly for a human program, that seems almost impossible with 1960s technology to imagine.